This video shows how to reverse engineer integer overflow attacks and apply security concepts into a legacy application. By creating a set of 4+1 views, we can discover vulnerabilities in the software that can be exploited. The next step is to transform an insecure legacy system into a secure target system. Before we inject security features into our source code, we need to draw a use case view showing a success scenario that demonstrates secure system behavior among all factors. We can see that a user can enter his credential, and upon successful checkout, the customer's account is deducted based on the purchase. The final customer's balance is displayed to the user for his reference. When a hacker attempts to enter a very large integer value on the item number or quantity fields, the system will display a specific error message to the hacker. Now we create our secure process view. In the insecure process view, we spot the exact location where the vulnerability happens. At that location, we need to perform 3 different input validations before the user input is processed. First, the application should check whether the item number and the quantity exceed the specified amount. Second, the application should check whether the user is allowed to make such purchases based on his or her balance. Third, the application should check whether the user inputs any other character except for integer to avoid system crashes. So, when a hacker attempts to inject a big integer value or any other invalid input, the system will display specific error messages to the hacker. The correct solution to integer overflow attacks is get the code right in the first place by performing good arithmetic hygiene, and in this case, restrict the maximum number of objects you'll create. Based on this quote from Michael Howard, we have to build methods to check the item number variable, the quantity variable, and the balance to avoid purchases without sufficient amount of money. There is no runtime exception generated for integer overflow, so you have to catch it yourself. Step 1 is creating the custom exception class. First, we need to build a custom exception class for each catch. This view shows invalid item number exception class. This view shows invalid quantity exception class. And this view shows the negative balance exception class. The second step is creating a method that throws a specific exception. We need to create methods that handle the overflows by examining all the lengths. The third step is making the try-catch statement in our main function. We simply call the method that we create in step 2. Notice that we catch not only the invalid quantity exception, but we also catch the input mismatch exception. Now we perform some testing. First, we try to choose an item that is not in the list. We can see that the invalid item number exception is caught by the application. Second, we try to underflow the customer balance variable. We can see that the invalid quantity exception is caught by the application. Third, we try to overflow the store balance variable. We can see that the invalid quantity exception is again caught by the application. Fourth, we try to perform a denial of service attack. We can see that the input mismatch exception is caught by the application. Lastly, we try to make a purchase without a sufficient balance. We can see that the negative balance exception is caught by the application.